This question is dealing with the rational numbers under addition. So automatically, if we're going to check to see if it's a group, we don't need to verify the associativity condition, because you have 4 basic conditions for a group: closure, associativity, identity, and inverse. And all of these questions seem to include 0, so we don't really need to bother with that, the identity condition. So what we're really concerned with is closure and inverse. But of course, if closure fails, then it doesn't matter. None of the other properties would make any difference. So let's check closure first. So in part A, the set of rational numbers including 0 in its lowest terms whose denominators are all odd. Is this closed? Well, it does seem to be, because if you have A over B plus C over D, then what do you get? You have your denominator BD, and then you have whatever goes on top here, the usual addition of rational numbers, and that is satisfying the definition here because denominators are odd, B and D are odd, so their product is odd. And there you have it. You don't need to check anything else for closure. The identity is clearly present, inverses are present, okay, and associativity holds. So automatically this is a group. So yes, this is a group. The set of rational numbers including 0 in lowest terms whose denominators are even. What about this one? This also holds the same way, because if the denominators are even, when you add it up, you take the product of the denominators when you're bringing them to a common value. So you have A over B plus C over D. You're adding that up. It's BD at the bottom. So B and D are even. Their product is even. And we have closure. You can easily see this. And of course, the 0 is there. The inverses are there. Associativity is there. So again, yes, this is a group. The set of rational numbers of absolute value less than 1 is a bit different. Here we do not have closure, and it's pretty easy to see that. What if you took something like a half and 4 over 6? Well, both of those obviously have absolute values less than 1, but when you add them up, it's going to end up being 7 over 6, and that absolute value is definitely not less than 1. So it fails. This is therefore not a group. The set of rational numbers of absolute value greater than or equal to 1 together with 0, that also fails. How can you see this? Well, you have minus 7 over 8 and let's say 5/4. Both of them have absolute value greater than or equal to 1, but their sum is 3 over 8. And of course, that absolute value is less than 1. So this closure fails, and therefore this is not a group. And part E, the set of rational numbers with denominators equal to 1 or 2. What's that? Well, that seems to be a group, because clearly it has 0, right? Because 0 has a denominator of 1. 0 is the same thing as 0 over 1. They have their inverses, because the negative ones are included. The negative numbers with denominators 1 or 2 are included. And there's associativity of addition. Also, if you notice, something like A over 1 plus B over 1, well, that's just going to be A plus B over 1. Similarly, A over 2 plus B over 2 is going to be A plus B over 2. And if for some reason this ends up being a whole number, well, it's just going to be whatever, let's say Z over 1, which is just Z. So again, it's closed, and therefore this is a group. So yes. And for the last part, part F, the set of rational numbers with denominators equal 1, 2, or 3, that one doesn't look like it will be valid, because a half plus a third, what is that? A half is 3 over 6, 1/3 is 2 over 6, that gives us 5 over 6, which is clearly a rational number whose denominator is not 1, 2, or 3, and it can't be further reduced. So we can see that this set is not closed under that addition of rational numbers. So again, this is not a group.